we have Samuel Monnier,
Yeah.
who will tell us about global gravitational anomaly cancellation for five-branes.
Thank you very much, and thanks to the organizer for inviting me. So anomalies occur when a global symmetry of a classical field theory is not realized in the corresponding quantum field theory. And actually, if the global symmetry is supposed to be gauged, such an anomaly signals an inconsistency of the quantum theory. So as a result, they provide some very useful constraint on quantum field theories. So the particular case of global gravitational anomalies, the global symmetry is actually the isometric group of space-time, and the associated gauge symmetry is the group of diffeomorphisms. So because in a full theory of quantum gravity we expect the diffeomorphism symmetry to be gauged, then this means that the low energy limit of such a consistent theory of quantum gravity has to have vanishing gravitational anomalies. And in fact, the miraculous cancellation of local gravitational anomalies in string theory provided the first serious hints that string theory may be fully consistent as a theory of quantum gravity. In contrast, global gravitational anomalies are another type of anomalies that have been comparatively much less studied. And so some of my recent results about the global gravitational anomaly of the cellular field allow to start checking systematically this constraint in various field theories occurring in the context of string theory. And today I want to tell you about the world volume theory of the M5 brane. So this will provide, this is a new non-trivial consistency check of the consistency of M theory. It will be explained. Yeah. Okay, so here is a rough plan of the talk. So I will briefly review exactly what anomalies are. I will give you a very rough strategy about how we can compute global gravitational anomalies. Then I will say a few words about the M5 brane geometry. And then I will review the various contributions to the anomaly of the world volume theory of the M5 brane. So there is an anomaly inflow from the bulk of M theory. There is a part coming from the cellular field theory on the five brane, and a part coming from the chiral fermions. And once we have these three parts, we will sum them and see that they indeed cancel. Okay. So the setup is a Euclidean quantum field theory defined on some compact oriented manifold M. And so to detect its gravitational anomalies, we can proceed as follows. So we'll see the partition function as a function over the space of Riemannian metrics of M. We have a group of diffeomorphisms which acts on the space of metrics by pullback. And a gravitational anomaly is present if the partition function is not invariant under this action. So one way to see this, for instance, is that the word identity relates the variation of the partition function to the expectation value of the divergence of the stress energy tensor. So if this expectation value is non-zero, then the symmetry is broken. Another way is to see that it implies that the quantum effective action is indeed not invariant under the symmetry. Okay, so now the problem is that checking the invariance of Z directly is in general relatively hard, but there is a way around which goes as follows. So we can see Z as defining a Hermitian line bundle over the quotient M over G. So if we want to be careful, actually this quotient can be very badly singular, so we can rather see it as a G equivariant bundle over M. But well, for our purpose, there is no harm of thinking it as a bundle over this space. And Z, in this case, we see it as a pullback of a section of A. So now if we can find a Hermitian connection on A, which has both vanishing curvatures and trivial holonomies, then this means that we have a global trivialization of our bundle, and that Z is actually G invariant. So in all cases at hand, the anomaly bundle admits a natural connection for which we can find explicit formula. And so this is what physicists usually compute when they compute anomalies. So the local anomaly is exactly the curvature of this connection, and its set of holonomies is called the global anomaly. So we'll be interested in this set of holonomies of a certain connection over this kind of space. Okay. So what is the strategy to compute these global anomalies? So I'll be very rough, but just to give you an idea. So again, this global anomaly is a holonomy. So you have to pick a path in the space of metrics. And this path has to be the lift of a loop. So this means that its endpoint has to be related by a diffeomorphism. And from that, we can construct a mapping torus, which is a fiber bundle with fiber or manifold over the circle. We undo it with a certain metric. So remark that over each point over our loop, we have a metric in the fiber. So this is this metric. And we pick an arbitrary metric over the circle that we rescale by a factor epsilon. So now if we can find a manifold W admitting the mapping torus as a boundary, it turns out that we can relatively easily compute the holonomy of the connection from a certain geometrical data on W in this limit where the base circle blows up. So maybe if I just make a small picture. So we have our manifold M that we this is what I call MC, so this is the mapping torus. And then this would be W. So maybe this is the picture you have to keep in mind throughout the talk. So this is maybe a bit abstract. So let's take a concrete case. So in the case of a chiral fermionic theory, this bundle A is actually the determinant bundle of the of the chiral Dirac operator defined by the chiral fermionic theory. So these works show that actually the holonomy of the natural connection on the determinant line bundle is given essentially by the eta invariant of the mapping torus of MC. And using the Atiyah-Pato-Singer theorem, you can re-express this eta invariant in this way in terms of a certain Dirac operator on W, which is related to the Dirac operator on M, in terms of its index and its index density. Okay. So let's now review briefly the M5-brane geometry. So we consider a smooth, compact-oriented 6-manifold, which will be the word volume of the 5-brane, embedded in a smooth-oriented spin 11 manifold X, which is the space-time of M theory. We call N the normal bundle of M in X, and we require the following condition on the Stiefel-Whitney classes. So actually, the first one is a direct consequence of the fact that both our manifolds are oriented. The second one is a consequence of the fact that X is spin. And the third one is something required in order, it's actually an obstruction for the 5-brane to be able to source the C field of M theory. So it's actually equivalent to the vanishing of the Euler class of M, no, of N. Okay, so these are constraints that we have on the word volume of the 5-brane. So now, if we see the boundary of a tubular neighborhood of M in X defines a force sphere bundle over M, and we can define a natural metric on this force sphere bundle induced from the metric on X. We simply induce a metric on the tangent bundle of N, and then embed the force sphere bundle as the unit sphere bundle in N. So we have this. So let me complete the picture here. So here we had our manifold M. So now over this manifold we have a force sphere bundle which I call N-tiled. Okay. And we saw that we have a metric on this manifold. We can also define a C field on this manifold. So recall that the M-theory C field is described by a shifted differential character of degree 4, where the shift is given by the first Pontryagin eigenclass of the, of the M-theory spacetime. So practically, this means that we can use the following ansatz for the field strength of the C field on the force sphere bundle. So it has a part proportional to the first Pontryagin classes of tilde M, which is just this shift here. It has a second part which is given by a global angular form on M tile. So this is just a form that integrates to 1 when you integrate it over the force sphere of the fiber bundle. And finally, it has a part which is pulled back from the base manifold. And actually, this can show that this part is actually exact because it's trivialized by the field strength of the self-dual field on the five-brane. So as I explained, this so this part F is here because the five-brane is actually a source for the C field. So if you integrate around the five-brane, the C field, you get one. And it can be realized canonically also. Okay, so now we'll extend this setup actually to include also a mapping torus, which will be a force sphere bundle over this mapping torus, and a force sphere bundle over the manifold bounded, which will be the force sphere bundle over the manifold bounding the mapping torus. Okay, so we and we require that this force sphere bundle satisfies the same restriction on the Stiefel-Whitney classes. Okay, so I need also another important fact is that this particular class is actually a lift of the degree 4 Wu class to integral cohomology. Can also show that rationally this part is 0, and this means that half the Pontryagin class of of the force sphere bundle is a characteristic element for the wedge product pairing on on an 8 manifold without boundary. And so this data actually is required to define the self-dual field theory on the five-brane, and will play an important role in the anomaly formula. Unfortunately, I cannot say much more right now. Okay, so now let's look at the setup for anomaly cancellation. So first, let us determine what is the space of background fields. So I write tilde M to be the space of metrics on this force sphere bundle, which can be obtaining as explained from a metric on X. We also have a space of C fields on M tilde, which, as I showed you before, can simply be parameterized by 3 forms on M, because all these let me come back because of this formula here, and F is exact actually. Okay, so the space of background field is given by this product. The group of local transformation is actually composed by the gauge group, which acts on the gauge field, and the group of diffeomorphism of M tilde, which can be obtained from a diffeomorphism of X. And we write F for the quotient. Sorry? So the gauge field is a 3 form, it's the C field. Okay, so you can shift, this means a 3 form with integral periods. So you can shift the C field with a 3 form with integral period. How am I doing this time? Oh, okay, so so as I explained, so we start with a loop in F. C determine actually a metric and a C field on the fibers of a mapping torus M tilde C here. In fact, we can convert them to a metric and a C field on the full mapping torus. I won't go into this detail. We also have to assume that there exists an oriented force sphere bundle tile W over this. Sorry. Yeah. So. Yeah, so we have our force sphere bundle over the mapping torus, and we have to assume that there exists a manifold W bounding MC endowed with a force sphere bundle that I call tile W, which extends all our data and is also satisfies the same restriction on the Scheffel-Whitney classes that we saw before. So this is actually a non-trivial and probably hard Cobordis problem. So fortunately, we have to make this assumption to check the anomaly cancellation. So you can check the anomaly cancellation only when this Cobordis problem has a solution for now. So let me now describe all the ingredients in the coming in the anomaly formula. So first start with the anomaly inflow. So the anomaly inflow comes from the fact that the M theory contains a Chern-Simons term. And if we cut out the tubular neighborhood of the five-brane, this Chern-Simons term is actually not a gauge or diffeomorphism invariant on the space-time with the five-brane exercise. And so its variation is the anomaly inflow. Okay, so how do we compute that? So general facts about Chern-Simons term allows you to compute in this way. So remember, we have a loop in the space of background field. This defines the mapping torus whose fiber is the space-time minus with this. We have, if you want, a loop of space-time with the five-brane. So this defines a loop. No, mapping torus whose fiber is the space-time minus the tubular neighborhood of the five-brane, and its boundary is precisely this M tilde C. And so the variation of the Chern-Simons term can be computed by integrating the corresponding characteristic form over this 12-dimensional manifold, this boundary. And in fact, the integral property of this of the characteristic form allow to re-express this integral as an integral over W tilde. Now, from that, we can use the explicit form of G tilde and integrate over the force sphere fibers of W tilde to obtain the integral of a form over W. What we obtain is that. So in particular, this second Pontryagin class form comes from the integral of the third power of the global angular form. Now let's move to the self-dual field. So the self-dual field is described by a similar formula. So it's also the integral of certain forms over the W, which is these forms are in particular the Hirzebruch L genus and the square of the field strength of the C field restricted to the five-brane. And so if you express this field strength in terms of F and lambda, you get this formula. So I have to say that this formula has not yet been proven completely rigorously. But although in principle it could be off by a sign on certain loops, but for instance this would imply some anomaly for type 2b supergravity. So at least at the physical level of rigor, can consider it established. So we will assume that and see that the anomalies indeed cancel. And so a consistency check we can do is to check that global gauge anomalies vanish with this choice of formula, but I don't have so much time, so I think I'll skip that. Finally, we describe the fermion global anomaly. So we write S graphic for the chiral spinor bundle of M, Sn for the spinor bundle constructed from N. So in general, these bundles do not exist globally, but their tensor product is well defined. This is linked with the fact that the sum of the second Stiefel-Wechsner class of T, M, and N vanishes. And the fermions are real sections of this bundle. So there are so-called symplectic Majorana fermions. So you have a real structure here because you have a quaternionic structure on each of these bundles. So their product is a real structure. So again, the global anomaly is given by the formula I showed you a bit before. So D is the Dirac operator on W given by this particular combination. So as we extended N to W with the same constraint on the Stiefel-Wechsner class, this bundle exists as well. And ID is the index density for Dirac operator. Now, an interesting fact is that in 8 dimensions, the Dirac operator is real. So this bundle has a real structure. This one has a quaternionic structure. So the whole bundle has a quaternionic structure. So the index of D is actually even, and it does not contribute to the anomaly. So we can forget this term. Okay, and now we can finally sum up all the parts of the puzzles. Okay, so here we have all the terms. So this is the index density coming from the fermions. This is the part coming from the self-dual field. This is the part coming from the inflow, which was obtained by integrating essentially the characteristic form associated to the Chern-Simons term on the four-sphere bundle. So remark that lambda, we defined it as half the first Pontryagin eigenclass of the four-sphere bundle over W. So this means that this term cancels actually with this term. And the remaining terms are well known to cancel from previous work on the local anomaly of the five-brane. So we see that everything cancels. So the global anomalies of this five-brane cancels. So here we are. So at least when we can extend, we can solve this cobordist problem, we see that all the global gravitational anomalies cancel. Also, the same computation with W closed manifold also give a somewhat maybe more straightforward proof of the cancellation of local anomalies, in the sense that, for instance, we don't have to smear the five-brane, as was the case on some previous work on the local anomaly. And also this result trivially generalized to the other chiral five-brane, so in type 2A and heterotic E8 times E8, because they both can be straightforwardly lifted to M5 brane in some M theory background. So, okay, I'll stop here. Thank you.